Welcome to podcast number 6, where we are going to look at some of the different factors that affect the rates of reactions. We've talked about concentrations of things, but then we're going to talk about those a little bit more in depth than we have in the past. Then we're going to talk about other factors as well we mentioned earlier on. Well, let's think back to our collision model, right? Thinking about the fact that when we have two molecules coming together, they have to hit each other for a reaction to take place. If they're sitting apart from each other on different sides of the room, then nothing is going to happen. In this case, I have carbon monoxide and nitrogen dioxide as my reactants. When they collide together, right, then they're going to produce carbon dioxide and nitrogen monoxide. Notice that if I double the carbon monoxide rate, if I double the carbon monoxide concentration, I double the rate. If I double the nitrogen dioxide concentration, I would double the rate. That means that both of these have to be first order. So it's first order with respect to carbon monoxide and first order with respect to nitrogen dioxide. Right? And so I know the rate expression. Now, if I say that if I doubled, say, the carbon monoxide rate, and we say quadrupled, if I doubled the carbon monoxide concentration and we quadrupled the rate, then we would know that that would have to be a second order in carbon monoxide. So we can figure that out from that information. All right, well, what we find using kinetic theory, and we'll talk a little bit about that before the chapter's done, is that if every time a carbon monoxide molecule collided with a nitrogen dioxide, right, then they would collide with 1 times 10 to the 9th molecules in every second, and meaning that this reaction would take place so fast that we wouldn't even see the reactants. They would just be boom, we'd have products. And yet we can watch this reaction take place. All right, now it's still a pretty fast reaction, right? The half-life of it's about 10 seconds. Right, but still we know that not every collision is leading to a reaction happening. So we have to be able to account for that as well. Well, when we think about our collisions, right, why doesn't every collision lead us to having a reaction, right? Why don't we always get a product at the end of it? Well, one of those is because, right, we have to have these things that are called effective collisions, right? We have to effectively have the right things happening for our reaction to proceed. And so one of those things that we need to be effective is what we call the molecule sterics. They have to be properly oriented. Now, if you move on from this class, right, if you get that C or above and you move on, you go to organic chemistry. Don't ask me any questions about organic chemistry. I haven't done that in forever. The only thing that I know is if you're really stumped on a question, write down sterics and you got a shot at getting some points on it. Sterics just say that, right, we're in the right orientation. So our example that we like to use for something like this is, think if you have like a USB drive and you try to plug it into your computer. It has to be facing the right way for that to happen. And you know that 95% of the time, for some reason, it's facing the wrong way the first time you try it, right? But it has to be facing the right way for it to go in. Same thing with our molecules. They have to be facing the right way so that they can intermingle properly so that a reaction will take place. The other thing that has to happen is that our molecules not only have to collide, but they have to collide with enough energy to have our reaction happen. All right, think about this, right? Our molecules are some protons, right? And they're surrounded by these electron clouds. Well, as our molecules come together to collide, they're going to be repelled by those separate electron clouds. They have to come together with enough energy, right, or enough speed, right, enough kinetic energy so that they can overcome that repulsion and they hit hard enough for our reaction to take place as well. And so they have to have enough energy, and we're going to call that energy the activation energy for our reactants to become products. Here we have a figure showing our carbon monoxides and our nitrogen dioxides reacting together. All right, and so remember from our balanced equation that our carbon monoxide is going to steal an oxygen from the nitrogen dioxide to become carbon dioxide over here. All right, well, if the carbon comes in and it hits a nitrogen, it's not going to react with that nitrogen. What the carbon has to do is it has to come in and hit the part of this molecule that has an oxygen so that it can steal it away to become that carbon dioxide over here. And so that's what we mean by our sterics, is they have to be aligned properly for that to happen. And if they're not aligned properly, even if they have all the energy in the world, when they hit, they're just going to bounce off each other because this carbon monoxide is going to be like, I don't want to steal you, Mr. Nitrogen, right? I have to steal one of the oxygens there. On our next slide, we're going to see this activation energy diagram, all right, for carbon monoxide to nitrogen dioxide reacting together. And so I'm going to just go ahead and move on to that slide where I'm going to talk a lot about these things that are here, right? But you can come back and consult this as you study as well by looking over the notes that are on here. But all of this should be covered on that slide one way or the other. So here's our figure showing the transition state of our reactions. And again, our example here is where we have our carbon monoxide plus nitrogen dioxide are going to react together to produce carbon dioxide, and then we're left over with our nitrogen monoxide. Right? And so remember that first off, we had to have the right sterics in order for this to happen, right? They have to collide at the right angles with each other, but they also need to have enough energy. And so notice that, right, if they collide and they have a certain amount of energy, say, and they come up here and they stop here, then they're just going to roll right back down the hill and stay as reactants. They need to have at least the energy that's given here, all right? And so EA, right, that's our activation energy. They must possess at least enough energy so that when they collide, they're going to overcome that barrier. Right? They have to have enough energy so when they collide, they come up and they reach at least the top here. Then they can roll down the hill and become products. All right, when they're at the top, they're called either an activated complex or sometimes they're called the transition state. All right, notice that in the transition state, they're transitioning from being reactants to the products. It doesn't mean that they're one or the other yet, right? The carbon monoxide is starting to attract that oxygen to it, but it hasn't totally stolen it away yet. That only happens once it's a product. So up there at the top when it's that transition state or the activated complex, it just means that they're right in between, like not really exactly the reactants, not really exactly the products. All right, just like we learned back in probably chapter 6-ish, right, there's also our enthalpy change. That is the difference between our reactants and products. Notice that the enthalpy change does not include our activation energy. So again, right, we can look back to our figure, but note that that diagram looks a heck of a lot like the things that we've seen from chapter 6, although when we drew those before, we had reactants and products, and we did not have the activation energy included. That's basically what's new in these things. Right, is that we have to overcome that activation energy, and when we do that, we are forming that activated complex that is in there. Once we reach the top, right, it can either go back to make reactants or forward to make the products, right, depending on how much energy it has and whether it wants to continue on to be the products. And again, right, just like that in chapter 6, that enthalpy change is the difference between the reactants and products. We do not include that activation energy in the enthalpy change, right? But it's still, remember, negative delta H, positive delta H, right? Negative where the reactants have higher energy than the products, and positive products have higher energy than our reactants.